Hello, my name is Insaf Sechitra, and I am pleased today to present our work on walk-in cycle and walk-in phases extraction from videos using transfer learning. For most of us, walk-in seems to be a seemingly innocuous mode of locomotion. Human walk-in, however, has aroused the interest of scientists for centuries. Understanding how it works would make it possible to carry out more targeted diagnoses and detect certain pathologies. Analyzing kinematic data, such as the acceleration and the angles formed by the different joints of the leg, can be used by clinicians to assess the condition, treatment, and rehabilitation of a patient with complex musculoskeletal or neurological disorders, treat pathologies such as cerebral palsy, Parkinson's disease, dementia, femoral patellar pain syndrome, osteoarthritis of the knee, and tear of the tendon, or even recognize human emotions. In geriatric medicine, concerned with elderly accident prevention, people can be monitored by classifying their posture and therefore detecting any corresponding alarm situation, such as a fall. A walk-in cycle has usually standard deviations, with a stance period where a reference foot remains in contact with the ground, and a swing period where the reference foot advances until the next contact with the ground. And each period is then divided into phases. Each phase occupies a certain percentage in the walk-in cycle. In abnormal walk-in, this percentage is variable, and some phases can even be excluded from the walk-in cycle. Observe, for example, how normal people have a different walk-in scheme than myopathic patients, diplegic patients, hemiplegic patients, neuropathic patients, coriform patients, and Parkinsonian patients. This makes walk-in cycle analysis and walk-in phases extraction crucial steps for many diagnoses. For manual analysis, beside the huge amount of time and concentration required for the analysis of a human walk-in, the intra- and interclinician analysis variance for the same patient makes a standard classification difficult. For automatic classification, most available computer vision-based work of gait analysis are concerned with biometrics, which makes obtainability of annotated walk-in phases datasets for clinical purposes problematic. Indeed, clinical analysis of walk-in is usually based on data acquired using sensors or markers. However, according to clinicians, walk-in with installed sensors and/or in a clinical set can distort the patient walk-in, especially for young children. The best analysis for this kind of patients is to capture their videos walk-in ideally outdoor or at home, and to analyze them afterward. In this work, we aim to exploit the power of one of the world's most cutting-edge technologies, a deep learning model, for the task of walk-in phases classification. The proposed approach is intended to be used for markerless videos captured in uncontrolled environments. For this sake, we follow several steps. As said earlier, we noticed a lack of datasets dedicated to the task of walk-in cycle classification. Our first step was then to prepare our own dataset. We used videos from the pedestrian direction recognition dataset, along with some videos available in the internet. Frames of each video were analyzed visually and classified in their respective walk-in phase folder. Here are some examples of the content of the loading response and mid-swing phases. The following step is training a classifier based on the constructed dataset. Instead of training our model from scratch, we use a transfer learning technique. During training, the training loss is minimized and the classification accuracy maximized. The trained model used is the VGG16, and the output is a trained model with weights updated during training. Using the trained model, the last step is to validate the trained model on frames not seen during training. The first step of our proposed approach is the dataset construction. Recall that walk-in cycle is divided into 2 periods. Each period contains several phases. The load-in response phase occupies 10% of the walking cycle. It begins with the initial contact of the heel with the ground, the heel strike, continues with the reception of the body by the right leg, and ends when the opposite foot rises from the ground. The mid-stance phase occupies 20% of the walking cycle. It begins at the end of the previous phase and continues until the heel of the right foot rises from the ground, the heel off. The terminal stance phase occupies 20% of the walking cycle. It begins at the end of the previous stage, beginning of the heel off, and ends when the opposite foot makes its first contact with the ground. This is the heel strike of the second foot. The pre-swing phase occupies 10% of the walking cycle. It begins when the opposite leg makes full contact with the ground and when the right leg comes farther off the ground. The initial swing phase, with the abbreviation of feet adjacent, occupies 13% of the walking cycle. It starts from the raising of the toes, toe off, until the feet are side by side. The mid-swing phase, with the abbreviation of tibia vertical, occupies 14% of the walking cycle. It continues until the tibia is vertical to the ground. The terminal swing phase, with the abbreviation of next initial contact, occupies 13% of the walking cycle. It ends with the contact of the right heel with the ground. The last phase is the first phase of the following cycle. By observing each frame of each video of our dataset, we classify manually the phases and put each frame in its corresponding folder. Then, for each frame, we apply a background subtraction and morphological operations in order to isolate the human walking from the background, and rename all frames. Renaming is done so that we have a significant name for each frame. For the patient first, the patient number, then the phase number, the video number, the status of the frame, either original with the background or cropped, with only the human walking, original RGB frame or binary shape, and the frame number. This results in 800 images with 97 images per class in the training, which gives 679 images for training and 122 images for test. The following step is the training and classification. The model used is the VGG16 deep network. We use this model for its robustness in classification, the large community using it, which makes both the model and the documentation available, and because we target in this work to classify each frame instead of classifying a sequence. To adapt the network to our problem, we replace the last layer, initially set to 1000 classes, by a 1 × 1 × 7 dimensional vector, since we classify the walking cycle into 7 phases. We keep the rectified linear unit and the softmax functions for the network. Although using transfer learning, the number of parameters remains large. We hence choose in training to freeze the first layers and train only the 3 last layers for our classification problem. We adopt 2 types of training, a local training using our machines and a distant training using Google Colab servers. We choose 50 and 16 for the epochs and batch size respectively, and vary the cross-validation percentages and the dropout to analyze the performance of our network. The first comparison of local versus distant training showed that distant training is able to converge faster than local training. We hence carry on our training remotely. By comparing the dropout, we notice that both training and validation precisions are larger for the 0.4 dropout compared to 0.5. However, with the two-fold classification, 0.5 dropout seems to give better results for both training and validation. In the 7-fold cross-validation, 0.2 dropout precision for both training and validation is once again enhanced, and is even higher than that of 0.5 dropout. A summary of experiments show that the 2.0 model gives the best validation precision, This is the training with a 15% validation split and 0.2 dropout. It is shown to have the best accuracy compared to 4.5 model and 5.1 model. The confusion matrix for the best model, the 2.0, shows that images that are the most confused are the ones most visually similar and represent the phases that are mostly adjacent in the walk-in cycle. The difference between the training precision, however, with the validation precision can represent an overfitting. This is mainly due to the small size of the dataset. Beside the research part of the work, where we seek for the best classification model, we propose in this work a complete system for clinicians to monitor their patients. A backend application is performed for the data scientist, in which the model is trained and selected, and that was done with the help of Python-based libraries. And a front-end application with a database for patients management is developed using Java and SQL. Here we present some interfaces for choosing a patient, then choosing a video by precising the frame rate, and classifying the patient video. Top is an example of classifying a male patient outdoor, second an indoor walk-in male patient, and last a female patient walk-in outdoor. The clinician can navigate through frames of the video and press the button Classify. The face, initially empty, is then filled with the automatic classified face. Then, the clinician can modify the face. If the face was automatically misclassified, the new dataset can then be reused for training the model. As a conclusion, we can say that the classification results are still encouraging for clinical tests, and the integration of deep learning into gait cycle classification can be used in the near future. However, due to the small size of the dataset, the model suffers from overfitting. As a solution, we can think of retraining the model with images of automatically classified phases and corrected by clinicians through our system to exploit other convolutional networks or exploit recurrent networks. Several people have helped with the accomplishment of this work. We would like to thank doctors from Dwira Hospital for their precious explanations concerning the gait cycle and neurological diseases related to gait, especially for children patients, and for validation of the constructed dataset. We would also like to thank students for their help in annotating the dataset and in implementation. Thank you very much for your attention, and if you have any questions, please feel free to ask them. Thank you again.